So I'll be presenting my project on high numerical aperture EUV lithography. So here's a historical overview of how lithography has been changing over time. So we started with a wavelength of 248 nanometer. Previously it was larger than that. Then we kept reducing the wavelength of the light source we used for the lithography. And currently we use the extended ultraviolet ray, which is about 13.5 nanometers. And the latest adjustment to reducing the critical dimension is introducing the high numerical aperture optics that gives us better resolution. And it comes with a whole new setup of optics involved in lithography. So my project would be explaining some things about the backgrounds and the application of high NA EUV lithography. Moving on. So let's start by quantifying the change we have with high NA numerical aperture lithography. So you see there is a comparison between the current standard systems known as NXC by ASML and the new high NA systems known as EXC. The most critical parameter here is the numerical aperture, which we are increasing from 0.33 to 0.55. In optical terms, this is a massive 67% increase in the light collection angle. This increase directly impacts our resolution, allowing us to print features with 8 nanometer half pitch or smaller. So effectively, we can push towards 2 nanometer logic nodes. Okay, so to understand why we need high NA, we have to look at the governing equation of lithography. So on the left is the Rayleigh criterion, the basis of all the lithography improvements over the years. There's the critical dimension. To give a definition, is the smallest feature we can write or we can print on a silicon wafer, and it's directly related to the process factor, the wavelength, and the numerical aperture. So this is a little bit critical because so far we've already optimized the process factor K1 and wavelength of light. Now we are in extended ultraviolet. If we try to reduce it more, we move into the X-ray, which is not ideal. And so the only thing we are left here is the numerical aperture. So that was the latest modification in the scanner system. However, simply, can we just make the lens bigger and then get like a little smaller critical dimension? So UV optics are mostly reflective mirrors, or it's not refractive lenses. So if we move towards 0.55 numerical aperture, we introduce 3 major geometric problems. First, it comes with massive optics. The mirrors become enormous. Now, presently, a company named Zeiss makes all the lenses for the SML machines. But still, for the high NA, the lenses, sometimes it can weigh till 10 tons. So the massive optics is the first hurdle we need to overcome. Then we have the angle of incidence. So the light hitting the mask, it's a much steeper angles than before. And because the light comes in such a steep angle, the physical height of the patterns on the mask casts a shadow on itself. So there's a shadowing effect or 3D mask effects on the from the reflective optics and the shadowing effect of the mask patterns itself. Okay, this brings us to the most unique optical innovation in this system. It's called anamorphic optics. Solve the shadowing problem, engineers had to break the symmetry of the system. We couldn't just magnify everything by 4x and more. In the x-axis, we kept the standard 4x magnification, but in the y-axis, which is the direction of the scan, the incident light, we increase the magnification to 8x. So horizontal plane, we get 4x, In the vertical plane, we get 8x demagnification. As we know, our masks and the patterns we get, it's a reduction optic system in a lithography system, scanner system. So this squeezes the angles at the mask level, mitigating the shadowing effect because of the angle of incidence on the mask when the light is reflected. But there is a cost because we are magnifying 8x in one direction. Our image on the wafer is cut in half. This results in a half-field exposure size, which complicates how we design. Let's look at the light source. How numerical aperture systems are like photon hungry. Because we are printing smaller features, we are more susceptible to short noise, random variations in the number of photons. To fix this, we need a higher dose of light. So typically we use the laser produced plasma. By a high power CO2 laser, you have to hit a single droplet twice. First, to make it a more pancake shape, then you hit it at the second time with a CO2 laser. That creates the extended ultraviolet light. That is the basis of most, I think, currently all of the ASML EUV scanning system. As optical engineers, we know there is not such thing as a free lunch. So the penalty for high resolution is the depth of focus. So as we can see from the formula, the resolution scales linearly with the numerical aperture. So the depth of focus decreases quadratically. So we increase the NA twice, depth of focus goes four times high. So with a high numerical aperture, our depth of focus collapses to around 30 to 40 nanometers. This is incredibly thin, what we call a pancake focus. So this imposes a strict requirements on the rest of the process. So you have to have a better accuracy, precision on the stage itself. Okay, so the mechatronic engineer is, just to give a brief overview, the SML twin scan machines are presented here. So these are the machines that are pushing the technological limit more and more. So the most interesting thing I find in these machines is the extreme acceleration of the stages. So the wafer stage and the reticle stage, these move around 8 to 32 G acceleration, which is, I think, faster than some of the F-17s or like the fighter jets in the world. Okay, so finally, the scanner needs to have a better ecosystem to push beyond the critical dimension we have now. And this leaves us with three different points. So first is the stochastics. We deal with random printing failures due to photon statistics. So we need thinner photoresist and we need stitching. So since we print half fills, so we have to stitch the left and right side of the large chip together. And finally, the metrology. So, if you can measure something, you cannot manufacture it. So our ultimate target is to develop equally capable metrology inspections with the electron beams, so we can have a better ecosystem for the high-NA EUV lithography. Okay, thank you so much.